Welcome to my classroom. In this video, I will talk about eigenvalues and eigenvectors of matrix and their geometric interpretation. We know that the multiplication of matrices is quite tedious. If we want to find a higher power of a matrix P, we prefer to decompose the matrix into a form of QD Q inverse, where D is a diagonal matrix and its power is easy to find by the formula, which can be proved by using mathematical induction. The product of Q and Q inverse gives an identity that makes the calculation of the power of P relatively easier. That is, the way of the composition of P into QD Q inverse involves the ideas of eigenvalues and eigenvectors. The diagonal matrix D, the matrix Q, and its inverse can be obtained systematically in an algebraic way. What interesting is the geometric interpretation of the decomposition. I would like to share this idea with you in the video. Let me use an example for illustration of both the algebraic solution and the geometric interpretation. Decompose the matrix P into the form of QD Q inverse, where D is a diagonal matrix, and hence find P to the power 10. To decompose P into the form of QD Q inverse, first, find the diagonal matrix by solving the eigenvalue equation for lambda. The roots of the equation are the eigenvalues of P. Form the diagonal matrix D by putting the eigenvalues in the entries of the diagonal. Take D equals 2004. For each eigenvalue, look for the eigenvector. For lambda equals 2, consider the matrix equation. Compare the corresponding entries. Both equations reduce to x minus y equals 0. This equation gives an eigenline of P. Take a point on the line, say 1, 1. This point forms a position vector and is called an eigenvector of P corresponding to lambda equals 2. For lambda equals 4, consider the matrix equation. Both equations reduce to 3x minus y equals 0. Take 1, 3 on the line and get another eigenvector of P. Now, form the matrix Q by putting the eigenvectors into the columns corresponding to lambda. As the eigenvalue 2 is in the first column of the diagonal matrix D, place the eigenvector 1, 1 in the first column of matrix Q. Similarly, place the eigenvector 1, 3 in the second column, as the corresponding eigenvalue 4 is in the second column of D. Find the inverse of Q. The determinant of Q is 2, so the inverse of Q is. Therefore, the decomposition QDQ inverse is obtained. This result can be verified by doing the multiplication and get P back. Note that the decomposition is not unique. For example, for the equation 3x minus y equals 0, we chose the point 1, 3. We can choose another point like 1 over 3, 1. Different choices of the eigenvectors give different Q and thus Q inverse. But it doesn't matter. When we multiply QDQ inverse, we get P back in both cases. In fact, we can take a different diagonal matrix by swapping the place of the eigenvalues. That is, we can take D equals. Then we swap the columns of the eigenvector correspondingly. That is, Q equals. In general, if we take D as, put the eigenvector corresponding to lambda 1 in the first column of the matrix Q, and the eigenvector corresponding to lambda 2 in the second column. Although we have different answers for the decomposition, our target is to find the higher power of P. All the decompositions of P give the same answer of P to the power n, so it is fine with different answers of the decomposition. Using the original choice of matrix D and matrix Q to find P to the power 10, the answer is. You may use another decomposition of P to countercheck the answers of P to the power 10. We see how the decomposition of P works algebraically. But why it works? It can be explained with the geometric interpretation of the matrices involved. As mentioned in my last video, a square matrix is a linear transformation mapping a line to a line. The matrix P is clearly not a standard transformation. As P maps 0 to 0, we try to regard P as a non-standard scaling. That means the scaling is done not along both axes, but two skewed lines passing through the origin. Referring to the diagram, let the scaling factors along the lines L1 and L2 be lambda1 and lambda2 respectively. Consider a point xy on the plane. Let the image under the non-standard scaling P be x prime y prime. That is, the way to get the image is that project the point xy on the lines L1 and L2 by drawing the lines through the point and parallel to L1 and L2. The parallel lines cut L1 and L2 at 2 points and denote the length from the origin by x1, y1. Scale the lengths by lambda1 and lambda2 along the lines L1 and L2 to x2, y2. To find the image, from the cutting point at x2, draw a line parallel to L2. Similarly, from the cutting point at y2, draw a line parallel to L1. The intersection of the parallel lines gives the image x prime, y prime. We do not have a general form of a non-standard scaling, but we note a standard scaling is given by a diagonal matrix. According to the discussion in my previous video, a non-standard scaling can be done by taking a suitable transformation before and after the standard scaling. In other words, convert the non-standard scaling into the standard scaling. 3 transformations are involved. Step 1. Transform the lines L1 and L2 to the x-axis and y-axis respectively. Step 2. Take the standard scaling. Step 3. Transform the x-axis and y-axis back to the lines L1 and L2 respectively. The standard scaling in step 2 is represented by a diagonal matrix, say D. For step 1 and 3, they are inverse of each other. It is easier to find a matrix transforming the axis to the lines than the reverse direction. So if the transformation in step 3 is denoted by Q, then the transformation in step 1 is Q inverse. In other words, we have P equals QDQ inverse. To find the image of a point under the product, apply Q inverse to the point first. The following diagrams show how the image is found under the product QDQ inverse. Suppose x1, y1 is a point in R2. Step 1. By Q inverse, transform L1 to x-axis and L2 to y-axis. Then the point is mapped to x2, y2 as shown in the second diagram. Step 2. Take the standard scaling by D. Then the point goes to x3, y3 in the third diagram. Step 3. By Q, transform the x-axis back to L1 and y-axis to L2. We have the image x4, y4 in the fourth diagram. With the geometric interpretation of the decomposition of P into QDQ inverse, we can explain why the algebraic solution works. Let me use the matrix P in the previous example for the explanation. P represents a non-standard scaling, which is decomposed in the form of QDQ inverse, where the diagonal matrix D is given by the two scaling factors, and the matrix Q is given by the transformations mapping the axes to the two skewed lines. To find the scaling factors, that is to find lambda such that a non-zero point xy lying on a skewed line which is mapped to lambda x lambda y, that is, rewrite the equation. It is equivalent to solve the matrix equation for lambda. Since the point is non-zero, the inverse of the matrix P minus lambda I does not exist. That is, determinant of P minus lambda I equals 0. This is the eigenvalue equation, which is shown in the first line of the algebraic solution. The root of the equation are the eigenvalues of P. These two numbers, 2 and 4, are actually the scaling factors of the geometric decomposition of P. Now, to look for the skewed lines for the non-standard scaling, that is, to find two equations in x and y such that x and y form a point on the line and have the scaling. Like the working of the algebraic solution, the two matrix equations are reduced to two lines, x minus y equals 0 and 3x minus y equals 0. They are the eigenlines in the algebraic solution and the skewed lines for the non-standard scaling. Suppose we take the diagonal matrix D as 2, 0, 0, 4. Then, under the transformation Q, the x-axis is mapped to the line obtained from lambda is equal to, that is, x minus y equals 0. Choose a point on the line, say 1, 1, as the image of 1, 0, that is. Similarly, the y-axis is mapped to 3x minus y equals 0. Choose 1, 3 from the line as the image of 0, 1, that is. Therefore, Q is. Thus, we have Q inverse. The matrix P is decomposed geometrically in QD/Q inverse with the same result from the algebraic solution. We notice that the decomposition of P is not unique. It can also be explained in geometric way. The reason is the points chosen from the skewed lines as the images of the unit points 1, 0 and 0, 1 on the axis are not unique. For example, from the skewed line 3x minus y equals 0, 1, 3 or 1/3 1 can be taken as the image of 0, 1, that is, leading to different transformation Q. Also, 3x minus y equals 0 can be mapped to the y-axis or x-axis. Thus, the standard scaling can be. In other words, P can be decomposed in different ways. For the decomposition of P into QD/Q inverse, compare the results of the transformations and the corresponding results from algebraic calculation for further verification. Let us check with the point 6, 8 in the first diagram. Under Q inverse, the points goes to 5, 1 in the second diagram. Take D, the point goes further to 10, 4 in the third diagram. Take Q, the image is 14, 22 in the fourth diagram. Same as the image calculated directly from P. The following points summarize the discussion of a square matrix P. 1. The roots of the equation, determinant of P minus lambda I equals 0, are called the eigenvalues of P, where the roots are denoted by lambda 1 and lambda 2. 2. For each eigenvalue, deduce the matrix equation into a linear equation which is an eigenline. Take a non-zero solution from each equation. Denote them by x1, y1 and x2, y2, and they are the eigenvectors of P. 3. Geometrically, P is a non-standard scaling. The eigenvalues are the scaling factors. The eigenvectors are the images of 1, 0 and 0, 1 under the transformation Q, mapping the axes to the eigenlines. 4. P is decomposed into QD Q inverse, where D is a diagonal matrix with the eigenvalues, and Q is a matrix with eigenvectors, putting the 1 corresponding to lambda 1 in the first column. 5. Hence, P to the power n can be evaluated in this form, which is relatively easy. The following questions are given as an exercise for the consolidation of your understanding.